Okay, so in order to do a coordinate change with triple integrals to spherical coordinates, first we need to look at the Jacobian. And so I've done a lot of the algebra here for us, so we don't have to spend a bunch of time writing it out. But as you recall, the first row of the Jacobian, it's going to be the partials of x with respect to each of the variables. So this is the partial of x with respect to rho. This is the partial of x with respect to theta. This is the partial of x with respect to phi. And then we do the same thing, partial of y with respect to rho, y with respect to theta, y with respect to phi, same thing with z. And then it's just a lot of algebra. So what I'm doing now is rewriting this determinant out, and I actually use the bottom row to expand. That's why you're seeing the cosine, the 0, and this as the coefficients, because it's a little bit faster to expand with the bottom row. And at the end of the day, I'm just going to jump to a little bit of algebra for us to do and look at a picture. So from the algebraic standpoint, when we finish this, we're getting here in this part right here, I can factor out a sine of phi from both of these terms. So I'm going to get rho squared sine phi, and I can actually factor out a negative sine phi, that would be fine. And then I'm going to be left with cosine squared phi plus sine squared phi. So at the end of the day, I get negative rho squared sine phi. So what I put in my integrand is actually the absolute value of the Jacobian. So the absolute value is just going to be positive rho squared sine phi, which is what I'm going to put right here. And I would like us to picture why this is the volume element. So that's where this picture is going to be really helpful on the right. You can notice when we chop up in spherical coordinates, we're basically trying to figure out the volume of this new type of region. And we can approximate it by thinking of it as like a rectangular box. It's not, but for small theta, small phi, small rho, we'll just approximate it. So we're just going to come up with what is the length, or this height, times this width times this length. And so using geometry, we can see this height is just going to be delta rho. We can see this width is going to be delta rho, or excuse me, rho times delta phi, and then this width is going to be rho sine phi delta theta. And when you multiply this times this times this, we're left with this change here. My deltas turn into d rho, d phi, d theta once I take the limit in my Riemann sum. But basically that's a nice way of picturing these pieces. So here's one of the rhos, one of the sine, the delta theta. There's another rho, delta phi, so I'll put the rho squared there. And then there's the, there. Okay, so that's giving me that volume element. Then the other piece in changing variables that I just need to rewrite my integrand to be in terms of x, y, and z. And in spherical coordinates, we just showed that x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is just rho cosine phi. Okay, so now we're just going to talk through, I wrote it out here, we're going to talk through how we're going to find the limits of integration. In general, I really recommend, because of the types of regions we're going to be working with in this class, which is what I put here, we're going to be integrating over domains that are solids of revolution about the z-axis for the most part. And so your theta and your phi limits are going to be constants. So that means I really recommend that you just use the ordering d rho, d phi, d theta, unless you're instructed otherwise. And that means that I want you to picture for a fixed phi and theta, picture letting your rho start out the origin and increase out radially, and look at where it enters and where it exits the region. And then to get your phi and your theta limits, you're gonna hold, like to get your phi limits, hold theta and hold theta and rho fix and let your phi increase. And really this is where that analogy that I was saying of picturing your arm will really help. Just imagine fanning your right arm from your head out down towards your feet and see where the largest phi is of your region, or the smallest phi and the largest phi that you would hit in the region. And then theta, you're gonna just figure out the same way that you did with polar and cylindrical. So that one's not too bad. Let's try a couple of examples now. So first, let's go to a formula that you probably had memorized since grade school, which is the volume of a sphere. And I know you're thinking, I already know this. This is 4/3 pi r cubed, but now we can actually see why from the perspective of calculus. And so if this has radius A, let's actually walk through how we could do this in terms of a triple integral. All right, so we know our final answer. We know what we're heading towards. Volume is 4/3 pi a cubed in this case, but now let's see how we can show that. So in terms of a triple integral, we're going to call this whole region here E. And if I want the volume, I'm just going to be integrating dv. And we can now set up the bounds that would trace out this. We're going to switch to spherical. Trace out the bounds that would give us this sphere. Okay, so my integrand is going to become rho squared sine phi. That's the Jacobian piece. And then d rho, d phi, d theta is the recommended ordering I say you try unless we indicate otherwise. And so to figure out rho, again, you start and shoot radially outward and look at the smallest and largest row. In this case, rho is just going from 0 to a. To trace out the entire sphere, phi needs to go over its entire range, and phi is allowed to start at 0, which is up here at the positive z-axis, and it's allowed to range all the way down here to a value of pi. So phi goes, okay. And then theta is going to go all the way around, so theta is just going to go from 0 to 2 pi. And what's nice is now, because my bounds are all constants when I set this up, and because my integrand's a product of a function of theta and rho and phi, I can actually detriple this, just like we used to decouple with double integrals. So let's set up the detripled part. Okay, and we can see this, the only integral in there that's a little bit tricky is just the middle one, and it's not bad at all. And when we do that, we get back to what we knew or what we've learned since grade school, 4/3 pi a cubed. So I just wanted you to see a proof as to why or where that comes from this triple integral perspective. Okay, now let's try to find the average distance from a point inside the solid ball of radius 1 to the center. So I would like you to put this on pause. Let me sketch what we're doing first, and I want you to make a guess first before you do it. So it's always good to have a nice estimate here. Okay, so I have a solid ball, so I'm including the interior. It has radius 1. And I want to know what's the average distance, considering all the points inside the region, from that point to the center. So first, write down your guess. What do you think? Then put it on pause and try it out. Okay, so first we're trying to find an average value, and it's actually an average distance. So let's define the distance from any point. Distance from any point to the center is this function, square root of x squared plus y squared plus z squared. Oh, let's talk about your guesses. So a lot of times sometimes I've had students guess 1/2. I want you to notice though, the way that this is, that there's more volume further out. There's going to be more points that are further out here than inside, smaller in here. So you're going to expect that your average distance is greater than 1/2, just because as you move further away from the origin, there's more points inside that sphere. And so somewhere between 1/2 and 1 is a good guess, if you guessed anything like that. Let's see what we get actually. We know how to find an average value. An average value over a region is going to be the triple integral over the region. of the function that we're trying to find the average of, then divided by the total volume. And we already know the volume because that's what we calculated above, so we can just write that here. We don't need to do a triple integral if you can already do it from geometry. We did it above just to prove where that comes from, but in general, you can just make this kind of jump. This is the volume. All right, and then my numerator is just going to become this triple integral of this square root. So this is, because I'm integrating over a sphere, it's suggesting that we do a coordinate change. Let's switch to spherical and then set it up. So if you haven't already done that, put it on pause, see if you can come up with the integral we'd get and finish calculating. Okay, and so here I'm able to d-triple again, just like above. This integral, just like above, we already found out was 2. This one, right, my last one's going to be rho to the 4th over 4 from 0 to 1, which is going to be 1/4. And so this is all going to simplify to 3/4. So if you guessed the average distance from a point inside this ball of radius 1 to the center is 3/4, you were right. All right, let's revisit this example that we did last lesson, which is this ice cream cone example, and see how we could set it up in spherical coordinates. In fact, it's actually a lot faster and easier in spherical coordinates. So go ahead, put it on pause, switch to spherical, and calculate the integral. Okay, so let's talk through how we do this. We're going to start with changing the dv. So there's the Jacobian, and then d rho d phi d theta. And then for rho, so shoot your arrow radially out from the radially outward from the origin, and look at where it enters the region, which is just when rho is 0, and where it exits. And notice when I shoot it out, it's always exiting along rho is equal to 3. And then my phi, I would just look at starting up here. So what's probably actually a little bit easier to do when you're trying to set this up is, because I know theta is going to go all the way around 360 degrees, you probably could just look at this cross section right here, which is like in your ZR plane, just one random cross section that you're going to now rotate around. I would work with just that while you're setting up your rho and your phi bounds, because I think it'll be a little bit easier to see what's happening. Okay, so there's your rho that's starting at the origin, exiting when rho's 3. And then your phi, you can see that the smallest phi is going to be right up here along the positive z-axis. And then the largest phi is coming from this full angle. So we just have to figure out what that is. Because we know that this is the cone, z is equal to r, that's a nice way to be able to realize that this angle here has to be pi over 4. So that's what we're going to get for this top bound here. And then my theta just goes 0 to 2 pi. And then again, we can d-triple based on how this is set up, and we get the same answer that we did as last time.